Hi, everyone. So today's topic will be inequalities and norms. Inequalities are important because in analysis and in the topics that we're discussing, we often have to deal with when things are small or big. This involves coming up with lower and upper bounds. And a crucial thing is to estimate quantities. Uh, that's one of the motivations. Another motivation is that we are working in Euclidean spaces, Rn, with components x1 through xn, and xi are real numbers. And we need to define distances on here. And to verify that they're distances, we'll need certain properties. So first, I want to review a little bit what is a norm and what is an inner product. And then we will do some proofs relating to these and prove some of the crucial inequalities that you will use time and time again in this course and in other places. So first, a definition of a norm. A norm is a function from Rn to non-negative numbers, and it satisfies three properties. First is the zero property, or zero axiom, that states that for all vectors, for all elements of Rn, the norm is non-negative, and if the norm is zero, then the vector is equal to zero. So that's the zero property. Now, the triangle inequality states that for every pair of vectors, the norm of the sum is less than the sum of the norms. And the homogeneity states that for every vector and every scalar, if we multiply it or reflect it, this can have either a positive or negative sign, then the norm of that multiplied vector will just be the scalar, or the absolute value of the scalar, times the norm of v. You have to have the absolute values because the quantity has to remain positive. So a simple example of this, we'll see others, is that if n is equal to 1, and if you're just on R, then norm of x, in this case x is a scalar, can be defined as just absolute value of x. And this is essentially the only norm that you have on R. And these properties are very easy to verify in this case. Well, the absolute value is non-negative, and absolute value being equal to 0 means that the scalar has to be equal to 0. The only case where absolute value is equal to 0. And the other properties are easy to verify as well. The hardest one is this triangle inequality. But that can be verified by doing a case check, depending on the V and W positive and negative. Now, in general, where do you get norms? Well, a good source of norms is another concept called an inner product. An inner product has four properties: symmetry, meaning that inner product of V with W is the same thing as inner product of W with V. Linearity, this is true for both components, but via symmetry. But so I'll write it only with one. So AB plus BW inner product with Z is the same thing as A V inner product with Z plus B W inner product with Z. Here, V, W, and Z are elements of Rn, and A and B are scalars in R. Non-negativity means that if I take an inner product with the vector itself, I get something non-negative. And the zero axiom is that if V inner product with itself gives 0, then V has to be equal to the 0 vector, meaning the vector of all zeros in the space. So just to highlight that, 0 vector is the one where you have n components equal to 0. So in Rn, the most common inner product that you choose is the so-called L2, standard L2 inner product. And it's defined as a sum depending on the components. So we have to label the components. V is the vector of V1 through Vn. W is the vector of W1 through Wn. And the inner product is defined as Vi times Wi. And well, it's easy to verify many of these properties. I won't do all of them. So, for example, non-negativity. So, for example, non-negativity. If I take V in a product with V, this gives me sum of I equals 1 through n of Vi squared. Now, each of these squares is non-negative, so the whole thing is non-negative. This gives property 3, and property 4 would follow because Vi squared is equal to 0 implies that Vi is equal to 0 for all I. And you have a sum of non-negative numbers, so they all have to be equal to 0. A complete proof would do that more carefully. This is a sketch of the argument. Now, norms induced by inner products. Whenever you have an inner product, you can define a norm by taking the square root of the inner product of V with itself. So, example, in Rn, then what we get is that the norm is equal to the square root of sum I equals 1 through n Vi squared, the usual norm that we get from the Pythagorean law. V1, V2, and then the hypotenuse is equal to V1 squared plus V2 squared. So in the n dimensions, you have n components. So this can be verified that this satisfies a norm, that this is a norm. So let's check that, and this time be a little bit more careful. So this norm, and sometimes this is denoted by adding a subscript. We'll see later what the subscript corresponds to, but for now, we'll just say that this exponent 2 is why we put a 2 subscript in this notation. So this defines a norm. Well, what is a norm? A norm is one that satisfies 3 properties: the non-negativity, the triangle inequality, and homogeneity. So we have to verify these properties. And 2 of these are fairly straightforward. Indeed, if V is in Rn, and we label its components, V1 through Vn, then the norm of V is square root sum I equals 1 through n Vi squared. Now, Vi squared are all non-negative, so the sum of them is non-negative. And if x is non-negative, then square root of x is non-negative. So square root of sum I equals 1 through n of Vi squared is also non-negative. Strictly speaking, the square root is not even defined unless we allow complex numbers for the negative numbers. So the first check is to make sure that it's defined, and then second check is to actually verify that by just using the properties of the square root function as they're defined. So indeed, the square root function is non-negative. Now we want to verify the second part of the zero axiom. If norm is 0, then v is the 0 vector. So suppose that the norm is equal to 0. That is square root I equals 1 through n, vi squared is equal to 0. But then what we get is by squaring, we get sum equals 1 through n, vi squared is also equal to 0, because the square of 0 is equal to 0. Therefore, 0 is less than vi squared is less than sum of these vi squared, which is equal to 0. So we get that vi squared is equal to 0, and ultimately for all I. And because vi squared is equal to 0, by taking a square root, we also get that vi must equal to 0 for all I. And this is what we wanted to show. So that's the first part. It includes two things: checking the non-negativity and checking that you actually get a 0. Now, triangle inequality, this is hard. Harder. So instead of doing it right now in this space, we will get it through some lemmas that I will do after this statement. But in the meantime, we'll finish the homogeneity. So homogeneity t times v is equal to absolute value of t times norm of v. So this proof, let t be a real number, let v be a vector. Well, if we take the left-hand side, this is square root of sum I equals 1 through n, t times vi squared. Now, you can pull out the t from the square, you get t squared. Then pulling out of the square root will produce absolute value of t times square root sum I equals 1 through n vi squared, which is the same thing as absolute value of t times v2. So by this calculation, we've shown that this is equal to that, and this worked for all t and v, so therefore it's shown for all t and v, and the proof is complete. So with this, we're left with verifying the triangle inequality. Now, the triangle inequality involves a couple of tools to prove it. The first is a very important inequality in and of itself, called the Cauchy-Schwarz inequality. And what it states is that if you have an inner product on Rn, and maybe this is a point to mention that whenever I say Rn, this could be any vector space. It could be finite dimensional. It could even be infinite dimensional. This is true on any inner product space. But for now, and for most of you, you will want to just think of Rn for now. So if you have an inner product on Rn, then always it's true, the following inequality is true. If you take V and W, absolute value of that inner product, this is less than or equal to the norm of V times the norm of W, where the norm is the induced norm from that. So specifically, square root of absolute value of V with V, or inner product of V with V, and square root of inner product of W with W. So this is the statement, and you need to give a proof. So there's a very nice trick here that connects to optimization and many other things, is we define a function that we always know is non-negative, and that motivates the definition. So f of t is inner product of v minus t w with itself. Now, by non-negativity, For all t real numbers, we have that f of t is non-negative. Now, this is crucial. Now, if we use linearity, we should say define f. By linearity, f of t, another way of computing it, is inner product of b with itself. You FOIL the product. So inner product of v with itself. Then there was a cross term where you have to use symmetry. 2v inner product with w times t, and plus t squared w inner product with w. Here we used symmetry. Because when we FOIL things, we get v inner product with w, and we get w inner product with v. But they have the terms in opposite order, but here we want to merge those terms, and then we get a 2. And that. So there we are using symmetry without actually writing it out. So this isn't always a non-negative function. And the trick next is that this is a quadratic, and we can minimize a quadratic. So how do we minimize? We find where the derivative is equal to 0. In this case, t star is equal to v inner product with w divided by w inner product with w. And when we write this, whenever you write something with a division, there's a warning. You can't divide by 0. If you can't divide by 0, you have to check separately the case. If this quantity in the denominator would be equal to 0, then by the 0 axiom, w would equal 0. And then by linearity, as a consequence of linearity, we get that v inner product with w is equal to 0, and the inequality is automatic. Why? Because if we take v inner product with w, we get 0, and this is less than or equal to norm of v times the norm of w. Why? Because this is equal to 0. 0 is less than or equal to 0. So this is, we have to add this separate check, but now after that check, we can assume without loss of generality that inner product of w with w is not equal to 0. And then we define a t star. This t star, I'll say soon something about it, where it comes from. But if we plug in t star, f t star, and we simplify, you'll get different denominators for the middle term and the right-hand term. If you merge those denominators and cancel out a term, then what you get is inner product of v with v, w with w, minus inner product of v with w squared divided by inner product of w with w squared. Sorry, just inner product with w with w. Now, this is a non-negative, this particular value. So what we get from it is that the denominator, because w is positive, we get that v inner product with v, w inner product with w, minus v inner product with w squared is bigger than or equal to 0. And from this, the inequality follows by moving the terms on the other side. So v inner product with v W in product with W is bigger than or equal to V in product with W squared, and taking a square root. And then we're done. Okay. Now, a small thing about where did this choice come from? That choice was governed by minimizing this quadratic. So I did not write it that way because I didn't want to say anything about why the minimum exists or anything like that. It's not very hard to do that because in T, this function is just a quadratic. So you could prove that this is actually the minimizer of that quantity. Okay. Now, a corollary of this is the so-called Minkowski inequality. And that states essentially what we want for the triangle inequality, namely that norm of V plus W is bounded from above by norm of V plus norm of W. So let's prove this. So look at sum of V I plus W I squared. And we should start the proof with saying let V and W be arbitrary. But then we can start computing sum of Vi plus Wi squared. And we'll then group this in a little bit of a funny way. We'll take absolute value of Vi plus Wi and absolute value of Vi plus Wi. And then we'll apply Holder. We'll apply Cauchy-Schwarz with Ai being equal to this. Then we will use the usual triangle inequality to say that this is less than or equal to sum of Vi plus Wi times Vi plus sum of the first term times Wi. So here we used that Vi plus Wi, the second term here, is less than Vi plus Wi. Okay, so now we are in this stage. Both of these we can use Holder or Cauchy-Schwarz. So CS on both of these terms, what it gives us is sum of Vi plus Wi squared, square root. Both of these will have the same factor. And then we get sum of Vi squared, square root, plus square root of Wi squared equals 1. So we get this inequality. Now divide by square root sum equals 1, Vi plus Wi squared. And then we get square root of I equals 1 through n Vi plus Wi, because the 1 power here is canceled out by the half power is less than or equal to square root sum I equals 1 through n Vi squared plus square root sum I equals 1 through n Wi squared, which is exactly what we want. Vi plus Wi. Norm is less than or equal to norm of V and sum the norm of W. A small detail here when we divided, you should check the case where sum I equals 1 through n bi plus wi squared is equal to 0. But then again, the inequality is automatic. Good. Okay, and with this, we can finally complete our norm proof, and we can just say that this follows by Minkowski below. So these are the main inequalities that you will use all the time. I will upload another video on other norms that you may encounter sometimes, but since this is already 30 minutes, I will end this one here.